Welcome, space travelers. Tonight, we're heading to the oldest frontier in all of science. Not the first stars, not the first galaxies, not even the first atoms. We're going further than that. Tonight, we're asking one of the strangest questions a human mind can ask. What existed before the Big Bang? So get comfortable. Let the room go quiet. And for a little while, let's travel to the point where astronomy turns into cosmology. Cosmology turns into physics, and physics begins to fade into something stranger. Because this question sounds simple at first. What happened before the universe began? But the deeper you go, the less certain even the word before becomes. And before we get into the theories, we need to clear away one common misunderstanding. The Big Bang is not some old, shaky guess that scientists secretly stopped believing in years ago. The hot Big Bang model is one of the most successful ideas in modern science. We know the universe is expanding. We observe the cosmic microwave background, the relic radiation left over from an early hot phase, and we measure the expected abundances of light elements produced in the young universe. Those are not loose hints. Those are the pillars that made the Big Bang model the standard picture of cosmic history. But there is an important nuance here. When physicists talk about the Big Bang, they usually do not mean a conventional explosion from a point into empty space. They mean that the universe was once in an extremely hot, dense state and has been expanding and cooling ever since. And while modern cosmology strongly supports that early hot phase, NASA also notes that scientists still are not sure what came before inflation, or even what powered inflation in the first place. So the hot Big Bang is on solid ground. The absolute beginning of reality is not. That difference matters. Because tonight, we are not asking whether the early universe was hot and dense. It was. We are asking whether that hot, dense beginning was the first thing that ever happened, or whether it was only the first chapter we can currently read. And to answer that, we need to step into a part of cosmology where the theories become bolder, the evidence becomes thinner, and the question itself starts to bend. Some of the theories we'll cover say there really was something before the Big Bang. Another universe, a contracting phase, an inflating background, a previous cosmic cycle. Others say the question is wrong from the start, that there was no earlier moment because time itself, in the form we recognize, did not yet exist. And that may be the strangest possibility of all. So in this journey, we're going to move through the best serious ideas modern physics has produced. Not internet mythology, not clickbait fantasy, not they erased this from history. Real theories, real cosmologists, real mathematical frameworks, some elegant, some deeply unsettling, some surprisingly beautiful, and none of them fully confirmed. By the end, we'll have a clearer answer to three things. What the Big Bang really means, which theories about a before are taken seriously by physics, and which of those theories might actually leave traces we can test. So let's begin with the first thing that makes this whole subject so difficult. Because to ask what happened before the Big Bang, you first have to know what time is allowed to do. Why before may be the wrong word. In everyday life, before feels obvious. Breakfast came before lunch. Yesterday came before today. Your childhood came before this moment. Time seems like a river. One event upstream, another downstream. But in modern physics, time is not a universal stage sitting outside reality. In general relativity, time is woven together with space into space-time. It bends, it stretches. It depends on motion and gravity. And if you push general relativity all the way back toward the earliest moments of the universe, the theory eventually drives you toward a singularity, a place where density and curvature blow up and the equations stop being physically usable. That is one reason cosmologists suspect that classical relativity alone cannot be the whole story at the beginning. So even before we get into exotic models, there is already a warning sign. The mathematics of our best classical theory reaches a limit, and once you arrive at that limit, asking what happened before may not be like asking what happened on the previous page of a book. It may be more like asking what is north of the North Pole. The question sounds grammatical, but nature may not owe it an answer in the form you expect. That is one reason inflation became so important in cosmology. Inflation is the idea that the universe underwent a brief burst of extremely rapid expansion in its earliest fraction of a second, helping explain why the cosmos looks so smooth and so nearly flat on large scales. It is a leading framework, and observations are broadly consistent with it. But the key point for our story is that even inflation may not fully solve the origin problem. The Borde-Guth-Vilenkin result argues that space-times, which are, on average, expanding, cannot be extended indefinitely into the past. In other words, inflation by itself does not automatically give you an eternal past. Something else may still be needed at the boundary. That result is not the end of the story. It does not tell us exactly what the boundary is. It does not prove a singular beginning in every possible theory. And it does not eliminate bouncing or emergent models that try to evade its assumptions. But it does tell us something important. You cannot simply say, "Oh, inflation takes care of it," and walk away. The question survives, and that survival is what opened the door to all the theories we're about to explore. Some try to remove the boundary entirely. Some replace the bang with a bounce. Some imagine our universe as one local event inside something larger. And some say the Big Bang was neither a beginning nor a bounce, but a transition between cosmic eras so different from our own that ordinary language barely applies. What makes this topic so fascinating is that every theory is trying to solve the same basic problem. How do you describe the universe at the point where the old equations fail? Do you quantize it? Do you replace the singularity with a bridge? Do you say time curved shut? Do you say our universe was born from a wider multiverse? Do you say another aeon came before our own? Physics has not agreed on the answer, but it has produced some extraordinary possibilities, and the first of those possibilities does something almost shocking. It doesn't tell you what came before the Big Bang. It tells you that, in the deepest sense, nothing did. Theory 1. The no-boundary proposal. If you want the cleanest and most philosophically radical answer in cosmology, this might be it. The no-boundary proposal, associated with James Hartley and Stephen Hawking, says that when you treat the universe as a quantum system, its wave function can be calculated by summing over geometries that have no boundary to the past. In the language of a modern review, the universe becomes finite, self-contained, and the Big Bang singularity is avoided. That sounds abstract, so let's slow it down. Imagine you are standing on Earth and asking where the edge of the planet is. If you live locally, that question makes sense for a continent or an ocean. But for the surface of the Earth as a whole, there is no edge. The surface is finite, yet unbounded. The no-boundary idea tries to do something a little like that for the origin of the universe. Not with ordinary three-dimensional space alone, but with the full geometry relevant to the very early cosmos. In simplified versions of the proposal, time near the beginning can behave less like the time we know and more like another dimension of space. The universe does not begin with a hard, singular edge. Instead, the geometry closes off smoothly. So when you ask, what happened before the Big Bang? The answer may be, there was no earlier classical time for anything to happen in. This is why the proposal fascinates people. It does not just move the beginning farther back. It tries to dissolve the beginning as a sharp wound in the equations. There is no cosmic wall, no literal first-second hanging over empty nothingness, no moment where the laws of physics suddenly switch on like a light in a dark room. Instead, the origin becomes a quantum geometric condition, a smooth closing, a universe that is not created after something else, but is self-contained. That makes the no-boundary proposal elegant. it also makes it difficult, because elegance is not the same thing as proof. The proposal lives inside quantum cosmology, where we are trying to describe the universe itself with a wave function. That is already a hard conceptual space. Then you have to decide how to extract probabilities from that wave function, how to connect the formalism to inflation, and how to interpret the path integral over possible spacetimes. Recent work in 2026 revisited how the no-boundary proposal should be evaluated and found that the probability story can change dramatically depending on how the gravitational path integral is treated. So even within this framework, there are active debates about what the theory really predicts. Still, as a serious answer to the before question, the no-boundary proposal remains one of the most important because it confronts the problem at the deepest level. It does not say there was a previous universe crashing into ours. It does not say a hidden space was inflating elsewhere. It says your intuition may be the problem. Maybe you are demanding a before from a regime where classical time has not yet emerged. That is both the strength and the emotional difficulty of the theory. It is powerful because it removes the singular edge. But it is hard to picture because the human mind wants narrative. We want a prequel, a cause, a prior state, some earlier stage where we can imagine a clock already ticking. The no-boundary proposal denies us that comfort. It says the universe may be like a story whose first page is not torn out, but curved so strangely that the beginning is no longer a sharp corner. And for some physicists, that is the most conservative answer available. But not everyone likes it. Some want a more explicit origin event, not just no boundary, but something like a quantum birth, a universe appearing from no classical space-time at all, which brings us to the second major answer. And this one is even more provocative in plain language, because it is often summarized in 4 explosive words: the universe from nothing. Theory 2. Quantum tunneling from nothing. Few phrases in cosmology are more likely to be misunderstood than this one, because when physicists say the universe may have tunneled from nothing, they do not mean ordinary empty space, not a vacuum chamber, not darkness, not a giant blank room waiting for a universe to appear. They mean the absence of a classical space-time background. No ordinary space, no ordinary time, no classical stage already sitting there. In the tunneling approach associated with Alexander Vilenkin, the universe is treated in a mini-superspace framework where the wave function can describe a universe emerging from vanishing size through a kind of quantum tunneling process. A modern treatment explicitly discusses the tunneling wave function in terms of tunneling boundary conditions, Lorentzian path integrals, and quantum tunneling from an initial universe of vanishing size. Now, quantum tunneling is a familiar idea in microscopic physics. Particles can cross barriers that classical physics says they should not cross. So the intuition here is not that the universe exploded out of literal non-being like a magician's trick. It is that, in quantum cosmology, the origin may be described the same way quantum mechanics describes other classically forbidden transitions. A universe can nucleate. A space-time can begin. Not because there was already time before it, but because the quantum description allows a transition from no classical universe to a classical expanding one. That makes this theory feel, at first glance, like a cleaner answer than the no-boundary proposal. You ask, what came before the Big Bang? And it says, not another classical world, a quantum origin. But as always, the closer you get, the stranger it becomes. Because this theory still does not really give you a before in the everyday sense. There is no older universe where events were happening normally, and then ours appeared. Instead, the prior state is not an earlier time slice inside a larger timeline. It is the absence of classical space-time itself. So in a subtle way, The tunneling proposal and the no-boundary proposal are cousins. Both are quantum cosmology answers. Both try to avoid the singularity as a simple classical beginning. Both say the question, what happened earlier, may be fundamentally misleading. And both face the same broad challenge. How do you turn a beautiful formal proposal into a definite, observationally tested origin theory? That is the hard part. Because the closer cosmology gets to the origin, the more it begins to depend on quantum gravity, and quantum gravity remains unfinished. We do not yet have a single, universally accepted theory that combines general relativity and quantum mechanics in a complete, experimentally confirmed way. So these proposals are serious, but they are also incomplete in a profound sense. They are maps drawn at the edge of a continent we have not landed on. That said, the tunneling picture remains one of the most memorable answers because it preserves something people crave: a genuine origin, not an eternal past, not a previous cycle, not a background multiverse that was already there forever. A beginning, but a beginning of a very different sort. Not first this happened, then that happened. Instead, classical time itself emerged from a quantum event. And once you hear that, another possibility naturally presents itself. What if time did not emerge from nothing at all? What if there really was a before? What if our expanding universe was preceded by a contracting one? What if the Big Bang was not the beginning, but the rebound? That idea leads us to one of the best-known alternatives to a singular cosmic birth: the Big Bounce. Theory 3. The Big Bounce and Loop Quantum Cosmology. Of all the theories in this video, this may be the one that feels most naturally satisfying to the human imagination, because it gives you what the mind wants: a real cosmic prehistory, a universe before our universe, a genuine earlier state. In loop quantum cosmology, a symmetry-reduced application of loop quantum gravity, the classical Big Bang singularity, is not the final word. Modern reviews describe one of the central results this way: due to the discreteness of quantum geometry, the Big Bang singularity is robustly replaced by a big bounce. Earlier foundational work in the framework likewise concluded that the Big Bang is replaced by a bounce, and more recent studies continue to treat the theory as predicting a bounce at the Planck scale that resolves the standard singularity. So what does that mean in plain language? In classical general relativity, if you run the clock backward, the universe gets denser, hotter, and smaller until the equations point toward a singularity. In loop quantum cosmology, that collapse does not continue forever. At extremely high density, quantum gravitational effects become repulsive enough to halt the contraction and reverse it. The universe bounces. A contracting branch becomes an expanding branch. Instead of a beginning from zero, you get a transition. Instead of a cosmic birth cry, you get a cosmic rebound. This is a beautiful idea for several reasons. First, it removes the singularity rather than treating it as a mysterious starting line. Second, it gives you an actual before, a pre-Big Bang branch. Third, it keeps the discussion inside physics rather than outside it. The origin is no longer, here the laws fail completely, but here quantum geometry changes the rules. And that matters. Because one of the deepest embarrassments in cosmology has always been that classical relativity works stunningly well almost everywhere, and yet when pushed to the origin, it predicts its own breakdown. The bounce says, good. That breakdown is the signal telling you to quantize the geometry. Of course, once again, elegance is not enough. You still need contact with observation, and this is where the bounce becomes especially interesting. Because unlike some purely philosophical origin ideas, loop quantum cosmology may leave imprints. Current work explicitly looks for observational traces of pre-inflationary loop quantum cosmology. in the cosmic microwave background, and reviews note that LQC remains consistent with observations while also being explored as a possible way to address certain anomalies. That does not mean the bounce has been observed. It hasn't. No experiment has yet forced cosmologists to say, yes, there was definitely a pre-Big Bang contracting universe. But it does mean this family of theories sits in an appealing middle ground. Not proven, not fantasy, potentially testable. And maybe that is why the bounce remains so popular in the public imagination, because it turns the Big Bang from a wall into a doorway. You can picture it. A previous universe contracts. Galaxies, matter, radiation, perhaps even entire cosmic histories are driven inward. Density rises toward the Planck regime. Then quantum geometry pushes back. Collapse becomes rebound, and our expanding universe begins on the far side of that event. Now, whether the pre-bounce universe looked anything like ours is another question. It may have been wildly different. Its matter content may have been different, its large-scale structure may have been mostly erased, its arrow of time may raise difficult questions. And even within bounce cosmologies, there are serious open debates about perturbations, entropy, initial conditions, and exactly how generic the bounce really is. But the core image remains one of the most compelling in cosmology. The universe did not begin. It turned around. And once you accept the possibility of contraction before expansion, another theory becomes possible. One that says contraction was not just a prelude. It was the key mechanism that prepared the universe itself. Not a violent collapse into chaos, but a slow, smoothing phase before the bang. This is the ekpyrotic idea, and it gives the pre-Big Bang universe a very different personality. Theory 4. The ekpyrotic and cyclic universe. If inflation imagines the young universe smoothing itself by blowing up incredibly fast, the ekpyrotic picture tries something far more counterintuitive. It says smoothing may have happened during contraction. In the ekpyrotic and cyclic framework, the Big Bang is not the beginning of time. A major review on the subject describes the Big Bang as a collision event, often phrased in higher dimensional versions as colliding brains, with an ekpyrotic phase preceding it. The same review states the idea bluntly. The Big Bang does not represent the beginning of time, and there was plenty of time before it for the universe to come into causal contact over large regions. That is already a major shift. In the standard story, one of the puzzles is why distant regions of the universe look so similar, even though they seem not to have had enough time to communicate. Inflation solves that by saying a tiny region once was in contact, then inflated enormously. The ekpyrotic scenario says maybe the universe had a long contracting history before the bang, so there was time for large-scale smoothing before our hot expanding phase ever began. In some versions, the picture is rooted in string, or M-theory, where higher dimensional brains move and eventually collide, igniting something that looks, from our perspective, like the hot Big Bang. In more stripped-down four-dimensional versions, the higher dimensional imagery is less important than the basic mechanism. A slowly contracting phase with a very stiff equation of state that suppresses chaos and anisotropy, preparing the universe for a bounce or transition into expansion. This is one of the reasons the ekpyrotic model has remained so attractive. It is not just trying to replace a singularity. It is trying to compete with inflation as an explanation for why the universe is so smooth, so flat, and structured the way it is. And in cyclic versions of the theory, the implications become even more dramatic, because then the Big Bang is not a one-time event at all. Expansion, cooling, dark energy domination, contraction, smoothing, bounce or collision, hot Big Bang again. A universe not with one opening scene, but with many. That is cosmologically intoxicating. It gives reality rhythm. It replaces a single absolute beginning with recurring cosmic eras. It makes the universe older than the visible stars, older than the cosmic microwave background, older even than the hot Big Bang itself. And yet, the theory has never fully escaped its difficulties. Even the classic review emphasizes that ekpyrotic and cyclic cosmology are theories still in development, with aspects that gained or lost importance over time and with key issues still under active discussion. The bounce mechanism, the generation and transfer of perturbations, and the embedding in fundamental theory have all been sites of debate. So this is not a case where cosmology quietly solved the question and moved on. It is a live possibility, not a settled one. Still, there is something powerful about the image. Inflation says the universe began with a runaway, outward burst. Ekpyrosis says perhaps it was disciplined by contraction first. Inflation says the first act is explosive. Ekpyrosis says the first act is compressive. And in a long-form story, that contrast matters because it shows you how non-obvious the early universe really is. The cosmos does not come with subtitles. You can explain the same visible universe by making radically different assumptions about what happened before the first light we can see. But now we come to a theory that changes the question in another way. Not by replacing the beginning with a bounce, not by smoothing through contraction, but by saying our Big Bang may have been local, a regional event, a bubble, a pocket, one universe among many. And outside it, inflation may still be going on. Theory 5. Eternal inflation and pocket universes. This is probably the most famous before the Big Bang idea in modern popular science, and also one of the most controversial. The core intuition is surprisingly simple. Inflation is a period of accelerated expansion. In many models, once it starts, it does not end everywhere at once. It ends in some regions, producing hot expanding pocket universes, while other regions keep inflating. Alan Guth argued long ago that essentially all inflationary models lead to future eternal inflation, implying an infinite number of pocket universes. More recent theoretical work still treats eternal inflation as a live multiverse mechanism, though not an uncontroversial one. Now translate that into plain language. Our observable universe may not be the whole universe. It may be one bubble in a vastly larger inflating background. Inside our bubble, inflation ended and reheated the universe, giving rise to the hot Big Bang phase that eventually produced particles, atoms, stars, and galaxies. Outside our bubble, inflation might never have stopped, and elsewhere, other bubbles might have formed, with other laws, other constants, maybe even other histories. If that picture is right, then the answer to what existed before our Big Bang is not necessarily nothing. It could be an inflating space-time from which our local hot universe emerged. That makes eternal inflation feel like a natural extension of modern cosmology. But it comes with a catch so large, it almost swallows the theory. Because the same framework that produces infinitely many pocket universes also produces a measure problem. Once you have endless pocket universes and endless occurrences of events, calculating meaningful probabilities becomes extraordinarily hard. As one review of the multiverse problem put it, in an eternally inflating universe, anything that can happen will happen an infinite number of times, and the difficulty is how to compare infinities in a predictive way. That is not a minor technical footnote. It cuts right into scientific usefulness. A theory that can explain everything by generating every possible outcome risks explaining nothing in a predictive sense. And then there is the origin problem itself. Because eternal inflation may answer what happened before our local hot Big Bang, but the Bordeguth-Vilenkin result still hangs over the bigger picture. Even an eternally inflating space-time, if it is on average expanding, is not automatically past complete. So eternal inflation may push the question one level back without removing it entirely. That is why this theory feels both grand and evasive. It offers a cosmic landscape, a multiverse, a mechanism for endless new universes. But it may not be the final answer to the ultimate beginning. At best, it may say our Big Bang was not the beginning of everything. It was the local beginning of our bubble, and beyond it, the larger process continued. There is something almost mythic about that image. Reality as foam, universes budding off from a larger inflating sea, each one with its own hot beginning, while the background keeps breeding more. But whether that image is the future of cosmology or a beautiful dead end, still unclear. Because the farther a theory moves from directly testable features, the more cautious science has to become. Still, eternal inflation survives because it grows naturally out of inflationary reasoning and because it gives a compelling answer to our question at the local level. What came before our Big Bang? Maybe another era of inflation, maybe a larger parent space-time, maybe a process still ongoing elsewhere right now, but there is another theory that also gives a real prehistory, and it comes not from inflation, but from string theory. A theory that says the universe may have emerged not from a bubble in a multiverse, but from a low curvature, weakly coupled state that existed before the hot Big Bang. This is pre-Big Bang string cosmology. Theory 6. Pre-Big Bang string cosmology. String cosmology has produced many ideas over the decades, but one of the most distinctive is the pre-Big Bang scenario associated with Maurizio Gasparini and Gabriele Veneziano. The basic claim is that the hot Big Bang might not be the first physical stage of the universe. In the string pre-Big Bang picture, the universe can begin from a low curvature, weak coupling state and evolve toward higher curvature and stronger coupling until stringy effects produce a bounce or transition into the hot expanding regime we recognize as standard cosmology. Reviews of the scenario explicitly describe the hot Big Bang as being replaced by a hot Big Bounce and emphasize that the model is motivated by string dualities and allows very different initial conditions from the conventional inflationary picture. This is one of the most interesting before theories because it is not just a generic bounce. It is a string theoretic prehistory. The universe, in this view, did not start out as an ultra-hot fireball. It may have started in a cold, dilute, nearly trivial-looking state. Then, because of the dynamics implied by string cosmology, that state became unstable and evolved toward the high curvature regime that eventually transitioned into the hot Big Bang. In other words, the universe may have approached the Big Bang from the opposite direction than our intuition expects. Not from chaos to order, not from maximal compression to rebound, but from a very weak, thin, low-energy state into an increasingly excited and curved one. That is already a remarkable inversion. And it leads to something even more valuable, possible observational consequences. One reason pre-Big Bang string cosmology stayed relevant is that it can imply a distinctive gravitational wave background. Gasparini and Veneziano argued that the simplest versions tend to produce a very small primordial B-mode signal in the CMB, but can generate a stochastic background of gravitational waves with a blue tilt potentially accessible to gravitational wave observatories. More recent work has taken that seriously enough to test it against data. In late 2024, an analysis using the first 3 observing runs of Advanced LIGO and Advanced Virgo searched for the stochastic background predicted by pre-Big Bang cosmology and found no evidence for such a signal, though the resulting constraints still remained compatible with a smooth bounce version of the framework. That is exactly the kind of tension that makes a theory scientifically alive, not confirmed, not ignored, tested and constrained. And that matters because in a field this speculative, the difference between untestable story and risky physical framework is everything. Still, pre-Big Bang cosmology has not become the standard picture. Its transition from pre-Big Bang to post-Big Bang evolution is technically hard. Matching the scenario cleanly to observed cosmological perturbations is not trivial. And like much of string cosmology, it lives in a mathematical landscape far richer than our current observational leverage. But as an answer to our question, it is one of the most vivid. Before the hot Big Bang, there was another regime. Not empty nothingness, not necessarily a previous universe like ours, but a stringy phase of reality with weak coupling and low curvature that evolved toward a violent transition. The Big Bang, then, would not be the start of existence. It would be the moment our familiar cosmology turned on. A crossing point, a translation between two eras. And now, we come to the boldest cyclical idea of them all. A theory that does not just give us a previous phase or a previous universe, it gives us a previous aeon, and says the remote future of one universe may become the Big Bang of the next. Theory 7. Conformal cyclic cosmology. Few cosmological ideas are as intellectually beautiful and as disputed as conformal cyclic cosmology, or CCC, associated with Roger Penrose. The basic intuition is almost poetic. Take the universe all the way into its unimaginably remote future. Stars burn out, matter thins, black holes dominate, then eventually disappear through Hawking radiation. Distances become so vast and the physical content so diluted that the distinction between the infinitely large and the infinitesimally small may, under a conformal rescaling, begin to blur. In CCC, that late, sparse, almost structureless future of one cosmic aeon can be mapped into the Big Bang of the next. So the next universe does not emerge from nothing. It emerges from the asymptotic future of the previous one. In that sense, the Big Bang is not the beginning of all things. It is the crossover from a previous aeon into ours. Recent work on CCC continues to develop the crossover physics, including proposals involving a gravitational wave-dominated epoch. This idea is radical, but it has a very specific charm. Unlike some bounce models, it does not require the previous universe to shrink into an ultra-dense crunch. Unlike eternal inflation, it does not require an ever-branching multiverse. Unlike the no-boundary proposal, it does not dissolve the past into a purely quantum geometric condition. CCC says there really was a previous universe-like era, and that the end of that era became the birth of ours. That is one of the grandest continuity stories physics has ever proposed, and Penrose did not present it as pure metaphysics. CCC made concrete claims about possible observational traces in the cosmic microwave background, especially features sometimes called low-variance circles or Hawking points, supposedly linked to black hole mergers or black hole evaporation in a previous cycle. A detailed search in Planck and WMAP data, however, found no statistically significant evidence for those signatures with currently available data. The authors stressed that this absence does not mathematically disprove CCC, but it does mean the claimed signatures are not established. That is crucial, because CCC is often discussed in a way that makes it sound like the evidence already exists. At present, it does not. The theory remains imaginative and serious enough to study, but the observational status is weak. Even so, it deserves a place in this video because it represents one of the few genuinely different answers to the origin problem. It says the universe may be cyclic, yes, but not cyclic because it crunches and bounces in the old sense. Cyclic because the geometry of the far future can be reinterpreted as the geometry of a new beginning. That is a much stranger cycle, not a heartbeat, not a bouncing ball, more like a cosmic handoff. A torch passed from one eon to the next, and whether or not CCC is right, it forces you to rethink something basic. Maybe the words beginning and ending are less absolute than they feel. Maybe in the deep structure of reality, an ending can become a beginning without contradiction. And by now, you can probably feel what all of these theories share. Each one is trying to save physics from the singularity in a different way. No boundary says the beginning is smooth and unbounded. Tunneling says the universe nucleates quantum mechanically. Loop quantum cosmology says collapse rebounds. Ekpyrosis says contraction prepared the way. Eternal inflation says our Big Bang's local. String cosmology says a stringy phase came first. CCC says a previous aeon handed reality forward. Different paths, same wound in the equations. But now comes the question that decides how serious any of this really is. Can any of these theories be tested, or are we just decorating the darkness with beautiful language? How we might actually test what came before the Big Bang. This is where the story becomes both humbling and exciting. Because the truth is, our direct observational access to the earliest universe is limited. The cosmic microwave background comes from about 380,000 years after the Big Bang, and even though it carries precious information about earlier conditions, it is not a direct image of the first instant. Before Big Bang nucleosynthesis, our observational grip becomes far weaker still. Recent gravitational wave work explicitly notes that the history of the universe before BBN is an epoch from which we have no direct data. So if we want to test before the Big Bang theories, we usually have to look for indirect fingerprints. The first place to look is the cosmic microwave background. Tiny statistical patterns in its temperature and polarization can tell us about the very early universe. Planck's 2018 results heavily constrained inflationary models, while the BICEP-Hodgkick program has pushed the upper limit on the tensor-to-scalar ratio down to R0.036 at 95% confidence using BK18, meaning there is still no confirmed detection of primordial gravitational waves from inflation. That does not kill inflation, but it does mean the most dramatic smoking gun has not yet appeared. Why does that matter for our question? Because different pre-Big Bang theories predict different kinds of primordial structure. Some bounce models and loop quantum cosmology scenarios can affect the largest scales of the CMB or leave excited initial states for perturbations. Some string-inspired pre-Big Bang models predict particular gravitational wave spectra. CCC proposed specific features in the CMB, like Hawking points or low-variance circles. But current searches have not found statistically significant support for them. So the microwave sky is not just a photograph of the young universe. It is a crime scene, and cosmologists are still dusting it for fingerprints. The second place to look is gravitational waves. This may be the single most important future path in the whole subject. Why? Because gravitational waves can, in principle, travel to us from eras far earlier than the formation of the cosmic microwave background. That means the earliest phases of the universe may have left behind a stochastic background of primordial ripples in space-time itself. Pre-Big Bang string cosmology has already been constrained this way with advanced LIGO and Virgo. Cyclic and bouncing scenarios are also actively studied through their gravitational wave predictions. In other words, gravitational wave astronomy may become the tool that finally distinguishes some of these origin stories from one another. The third place to look is in the overall large-scale structure of the universe. How matter clusters, how space is curved, whether the primordial perturbations were purely Gaussian, nearly scale invariant, or carrying small anomalies. Inflation currently does very well on many of these fronts, which is why it remains the leading paradigm. NASA notes that inflation explains key observed features such as the universe's near flatness on the largest scales, and the Planck data remain broadly supportive of inflationary expectations. So any alternative theory has to work very hard just to match what inflation already gets right, and that is easy to forget when people casually say, maybe there was something before the Big Bang. Sure, maybe. But a real theory is not just a picture of a prior stage. It has to reproduce the universe we actually see. It has to explain why the cosmos is so smooth, why the fluctuations have the form they do, why light elements came out in the right abundances, why the CMB looks the way it does, why galaxies formed the way they did. That is the standard. And once you remember that, you start to appreciate why there is no winner yet. These theories are not just storytelling devices. They are trying to survive a firing squad of data. So where does that leave us? In a very honest place. The hot Big Bang is real. The origin beyond it remains open. And the field is divided between theories that try to eliminate the beginning, extend the past, cycle the cosmos, or enlarge reality beyond our universe. Which brings us to the final question. If you had to step back from all of this and ask which ideas feel strongest right now, what would the answer be? So what probably existed before the Big Bang? The most honest answer is this. We do not know, but that does not mean all ideas are equal. Some are clearly more serious than others. Some are mathematically motivated but observationally distant. Some are elegant but hard to interpret. Some are testable in principle and therefore especially valuable. If you ask which answer is the most conservative, it may be the no-boundary family of ideas, because it does not demand an entire prior universe in a classical sense. It simply says the very beginning may be quantum, smooth, and unbounded to the past. It solves the singularity problem by changing what the origin even means. If you ask which answer gives the clearest physical prehistory, it is hard not to point to the bounce models. Loop quantum cosmology, in particular, offers a very direct story. A previous contracting branch, quantum gravity effects, then rebound. It is attractive because it preserves a real before while remaining tied to an actual quantum gravity program. If you ask which answer is most grandiose, that is probably eternal inflation. It transforms our Big Bang from the birth of everything into the local birth of one pocket universe among many. But it carries serious conceptual baggage, especially the measure problem, and may not solve the absolute beginning anyway. If you ask which answer is most visually and philosophically compelling, many people would choose the ekpyrotic or cyclic universe, or Penrose's conformal cyclic cosmology. Both say the Big Bang was not the first page. Both restore a cosmic past. Both replace a singular start with continuity, but both remain outside the mainstream standard picture, and CCC in particular lacks confirmed observational support in present CMB searches. And if you ask which theories have the clearest path to being constrained by new data, the answer may be the ones with gravitational wave predictions and CMB signatures. Some bounce models, some string-inspired pre-Big Bang models, and perhaps refined cyclic scenarios. That is where the next real progress may come from, but maybe the deepest takeaway is simpler than all of that. The Big Bang may not be a wall, it may be a fog bank. For most of the 20th century, it was tempting to speak as though the Big Bang simply was the beginning. Full stop. Now the situation is more subtle. The hot, dense early universe is well established. What happened at the boundary of that phase is not. And so modern cosmology has split into different philosophies of origin. One says there was no ordinary before. One says space-time tunneled into existence. One says collapse rebounded. One says contraction prepared the world. One says our universe is one bubble in a much larger process. One says a stringy phase came first. One says the previous aeon handed the cosmos forward. 7 doors. No final key. And maybe that is exactly what we should expect. Because the question is not small. It is not even merely ancient. It is the question behind all beginnings. Not where did Earth come from, not where did the sun come from, not where did galaxies come from, but whether reality itself had an earlier state, whether time had a parent, whether the universe began, rebounded, emerged, or inherited itself. And for now, the truth is that science is still traveling, still measuring the microwave sky, still listening for primordial gravitational waves, still trying to understand whether inflation had a beginning, whether quantum gravity replaces the singularity, whether the past is finite, cyclic, or something even stranger than either word suggests. So maybe the best final answer is not a single theory. Maybe the best final answer is a change in perspective. The Big Bang was almost certainly not the moment when physicists get to stop asking questions. It was the moment when the questions become hardest. The visible universe gives us one clear message. There was an early, hot, dense phase, and it happened. But the frontier beyond that is still open, and some of the most brilliant minds in science are still arguing over what lies on the other side of it. And I think there's something deeply beautiful about that after everything we've learned about stars, black holes, galaxies, relativity, quantum fields, and cosmic history, we can still arrive at the edge of the map, look into the oldest darkness of all, and honestly say we are not done, not even close. Thank you for traveling with me through this one. This has been Space Traveler, and tonight we went as far back as modern physics can responsibly take us. Not to the first second, but to the place where even the idea of a first second begins to come apart. And somewhere beyond that boundary, whether there was a bounce, a quantum birth, a previous ion, an inflating sea, or no ordinary before at all, the universe keeps its oldest secret a little longer. Until next time, keep looking up.